Okay, so here we are. Last time we were talking about integrals and spherical coordinates. And we did one example. Quick reminders, again, this is a segue back in, of always this order. Again, there is some extremely weird, manufactured, unnatural counterexamples. For all practical purposes, always use this order. Again, don't forget the stretching factor. You'd be surprised how easy it is to get distracted by all of the drawing of the pictures and the thinking about the slices and the bounds. It's really surprisingly easy to get distracted by that, to forget your stretching factor. My defense against this, that I urge you to consider, is to always write this down all at once. Don't ever just write down d rho d phi d theta by itself. You're just asking for trouble. You're gonna forget, right, that stretching factor if you're not careful. So that's something I hope you'll consider. So real quick, let's hit the broad strokes of the example we did last time. We're looking at this ball here, radius A, centered up on the z-axis here, so that it's sitting on top of the origin in the xy plane. And theta slices, of course, look like this. And, of course, they go all the way around on this particular domain, and so 0 to 2 pi for our theta bounds. To look at that theta slice, I'm going to redraw it. Again, I'm going quickly because we did this last time. There's that theta slice drawn, looking at it head on. You can see the slice itself, which is a little bit tricky to draw in the three-dimensional picture because we're looking at it at an angle. And it's much easier to draw in this redraw here, where we're looking at it straight on. Just makes life easier. So, looking at this, now let's think about phi slices. And phi slices, now of course remember phi is an angle measured off of the z-axis from the origin, something like that, right? But again, a little bit easier to see what's going on if we do that same thing off of the z-axis, measured at the origin, over here. And so looking at these kinds of slices, I think you can see that our very first slice is straight up, where phi is 0. And then they continue on until they finally run out at the ending value, pi over 2. So phi range, 0 to pi over 2. All right. And then, okay, now we're going to pick a phi slice of our theta slice. So we're looking only at this little ray coming out of there, and let's not forget, keep track of the fact that what that really is this ray coming out of the origin, right? We're just looking at kind of a more convenient representation of it here in this picture. And so let's see, where do we start? Well, rho starts at that point, aka this point, aka the origin where rho is equal to 0. Okay. And then where do we end? Where's the last, as we do our rho slices, where's my last point, in other words, on my phi slice of my theta slice? Well, it's this point right here, which is on our sphere. And so we're going to in order to figure out this upper bound for rho, we're going to have to actually find the equation of this sphere. And so now, a little bit of chapter 1 work to be done. You have a ball, the radius, the center. You write that equation, and a bunch of work to be done to get down to this. This is a matter of plugging in the conversion formulas, of course. And here's your equation of the sphere. Again, reminder, why are we looking at that equation of that sphere? Because my ending slice, my last value of rho, is on that sphere. So as I try to find my upper bound for rho, I need to solve for rho in this equation, and of course it's already solved for, so that makes life easy. And there you go. Okay, so how are we doing? Does everybody remember all this? Is everybody happy with this? Okay. All right. Okay. So, I do want to make a plug before we go on. Good picture it's just really critical, and for a couple of reasons. On the one hand, it will make your life easier. In fact, it's going to make your life tractable, right? I mean, without a picture, it's extremely hard to come up with these kinds of bounds. In fact, if you do it without a written picture, I'll bet you that you're doing it with a picture in your mind. Right? So a written picture, extremely helpful. Second reason, don't forget, it's not a question of whether your answer is right. You do have to show your reasoning. The reasoning on finding these bounds, these, d rho, d phi, d theta bounds, is geometric. It just is. Right? I mean, the counterexamples are prohibitively inconvenient. Borderline infeasible. So you got to give me some reasoning, of course. Again, that's one of the fundamental aspects of this course. And so a picture is unavoidably going to be part of that reasoning. So again, you've got to give me a picture as part of your answer so that I can see what your reasoning process was and thus understand how you got to the conclusions that you got to. Okay, so on the topic then of the picture you draw. I think too many students try to save paper and make a little picture about like this, about that big, right? Little adorable, little cute little picture. Don't try to squeeze it all into a teeny tiny little picture. Take up some space, right? Don't forget you've got the back of the page on the exam, for example. Right? It's all available space. So make yourself a nice big picture. Obviously, you want it to be as clear as possible. I'm a big believer in achieving that by drawing more than one in a revise, redo kind of strategy. So, in other words, draw a picture. It's going to be bad. Use that bad picture, though, to help yourself understand, wait a minute, so what does this thing really look like? Once you have a better understanding of what it looks like, you can draw a better picture, which might give you a better understanding of what it looks like, etc. Right? So this kind of bootstrapping approach can be really useful. Lastly, there are techniques. Right? This is not a matter of who was, just naturally gifted with the most artistic talent. Right? There are tricks and tips, things to know, techniques to practice that will make your drawings better. Find out what those techniques are, right? Make sure you know all the tricks. Give yourself that advantage, and then practice and give yourself the advantages of being able to actually develop the skills and the chops to be able to make decent pictures. Again, I have a couple of recordings on this on my miscellaneous topics playlist. That's everything that I know about how to do good mathematical drawings, and I hope you'll find that useful. And of course, there may be other resources elsewhere. You're also welcome to do whatever you want on that. Okay, so next example. Another ball, again of radius A, this time centered over here on the y-axis instead of the z-axis. Doesn't look like it's going to be very different. It's pretty different. And the reason for this is that spherical coordinates, of course, is not symmetric with respect to rectangular coordinates. The z-axis is special for spherical coordinates. So in fact, a very different question. And as usual, let's start with looking at theta slices. There, for example, is an example sample slice of our ball here. Okay, you can see what that slice looks like. I think it's a pretty easy pitch that if you take a planar slice out of a ball, you're going to get a disc, right? By the way, my advice on a question like this that you may encounter in a homework, or if you just want to, give yourself a physical, three-dimensional visual aid just to understand this exact example, bag of oranges is great, right? You can cut them up, right? Then you get to eat the oranges. It's win-win, right? So anyway, a slice looks like this. It's a disc. And now let's ask, for what values of theta do we get such discs? And I claim it's only for sort of 0 to pi. right? Our theta bounds are going to be 0 to pi, as noted there. Because if you go around further, if you're sort of going back into the back side of the XZ plane, there's nothing over there. There is no ball over there. Right. Did everybody see that? All right. Okay. Alrighty. So we know our theta bounds. So we're going to fix a value of theta. We're going to look at our theta slice. Again, here it is. And again, I'm going to redraw that picture, looking straight at it, so that I don't have the artistic challenge and the visualization challenge of thinking about angles while looking at a distorted picture that distorts angles. Right? That's inherently confusing. So here is my theta slice, and let's think about the phi slices. Again, a phi slice is measured off the positive part of the z-axis and measured at the origin. Right? So now drawing that over here, here's the positive part of the z-axis at the origin. Right? So we're thinking about these angles there. There's my phi. Try that again. Harder than it looks. There we go. There's our phi. Right, and I think it's a pretty easy pitch that the very first phi slice. I mean, if you look as theta sort of decreases, it gets small. Phi gets smaller and smaller. 0 is our starting value of phi, and then our last value of phi, as you increase and go further along, it just keeps going until you're going straight down, aka pi. Does everybody see that from the picture? Okay, so 0 to pi. And so let's document that then. Phi 0 to pi. Then we focus on a particular phi slice. That is, a particular phi slice of our theta slice. And on this phi slice, we now ask the natural next question, which is, what's the range of values of rho? And again, you just have to find the points and think about what they mean. This point here, well, don't forget, that's actually this point over here. It's the origin. Rho is equal to 0. Okay. And then the last rho slice is going to be this point here. What does that mean? Well, don't forget what that actually is. That's actually a point like over here, right? And what you again notice from the picture, gosh, it's so important to have a picture. The picture tells all, right? And it's from the picture that I see that this last value, this last rho slice, happens on the sphere. So again, we've got to do this whole chapter 1 thing. You take this sphere of radius A, blah, 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 and find the spherical equation. And so a bunch of algebra. Now, make sure you can do that. Right? That's all chapter 1 stuff, but chapter 1 was a long time ago, right? And so now is when we're going to be really using those ideas. So make sure that you're up to speed and, polished up and everything on that part. So again, looking for rho bounds. So I solve for rho, and there's our rho bound. Everybody happy? Now notice how much time we spent talking about the slices and the bounds and the equations and stuff, and wouldn't it have been easy after going through and doing all of that to accidentally forget that rho squared sine phi? Right? That's big points. Right? It's the big multivariable calculus concept. It's the most substantial, I'll say, multivariable calculus concept in the example. It's worth points. It's just unavoidably worth points. And again, glass half full, glass half empty. You can think of it as a risk of, I'm subjected to so much risk because of this one thing. No, glass is half full. You get so many points just for writing this one thing. Right? That's the way I encourage you to think about it. So again, make sure not to forget it. Said differently, make sure, please, to always write this down all at once, if only to help you, not forget. that stretching factor. If it makes you feel better, it is always natural to write that down all at once, because after all, that's what dV actually is. Right? d rho d phi d theta is not a thing. It's not important. It does not naturally arise in this question. So, okay. Alrighty. So here's the last example. This one I bring up just because it's a good example of a particular little trick I think is very handy. So anyway, let's get into the example. First, we're looking at the collection of points that are outside of this sphere. Right? So outside of that sphere. And then inside of this sphere. All right, so inside of the blue, outside of the green. Does everybody see how I got that? Okay. So, what is inside of the one and outside of the other? And, just you kind of have to use your geometric intuition, as is often the case in these kinds of questions. And it's this thing right here. I feel like it's a big warm winter cap or something like that. Everybody with me? Okay. So, I claim that's hard to draw. Now, what I just did here wasn't that hard, right? But notice my picture is actually quite poor, right? There is actually a kind of an edge or a lip or something kind of going around like this. That's just hard to see, isn't it? Let me just go ahead and draw that. Right, there's actually a sort of a visible lip there, and so really my solid it actually comes all the way down to here, but if I draw that whole thing like this, then it's sort of hard to see that there's a kind of an indentation at the bottom. I mean, this bottom sphere has taken a scoop out of the underside of the top sphere, the top ball. So it's just hard to make a good drawing of it. Your drawing's going to have significant imperfections kind of no matter what you do. That I've been able to figure out anyway. Maybe there's a better, something I haven't thought of. So, very hard to draw. Now you can see from this picture without too much trouble that, we're clearly, we've encircled this part of the z-axis. So theta goes all the way around. I think that's pretty believable. That part's okay. But what am I going to do to try to figure out the phi slices? In other words, when I look at this theta slice. Okay, so I visualizing the actual solid and then thinking about how the phi slices, I don't know, I find that pretty geometrically challenging. Okay, so here's my big trick. Rather than looking at the intersection, namely the actual solid itself, and then trying to take cross sections of it, which again I feel like is kind of hard. So I'm gonna, that's sort of a hard approach to do. Instead of doing that, it works just as well to look at individual cross sections. That's plural now. We're going to look at cross sections of the top ball and the bottom ball individually. Those are easy. These individual cross sections, if I look at the, let's see here, if I look at the top ball here, a theta slice of that ball, no sweat. It's a disc, or a half disc, right? It's just this right here. That's easy. And then likewise for the bottom. If I look at the bottom ball and ask, what do its theta cross sections look like? No problem. It's just a ball. Its cross sections are half a disc again. So draw those cross sections individually. And then look at the intersection of those individual cross sections. So in other words, you can do the slicing and the intersecting in kind of whichever order you want. It doesn't matter. It doesn't make any difference. And looking at this picture, and what is it that's inside of the blue but outside of the orange? No sweat. I see it right here in my picture. I accidentally drew it unwittingly as I was drawing these much easier cross sections. Everybody see how that works and why this is a useful point? Right? I didn't have to think as three-dimensionally. I didn't have to think about the hard part of the question in some sense. Three-dimensionally, I got to think about that two-dimensionally. So I think it's a really nice trick, and for your consideration, can be a real savior. And so with that noted, I'm going to go ahead and now again draw our cross section here. This is our theta cross section. So, wrong. This is our theta cross section. Okay. And now we start thinking about the other stuff. And so, the rest of this is pretty typical. Let's think about the range of values of phi. Here's our phi slices. Again, easy mistake to make. Don't put your center at the location of whatever your round thing is. That's, again, not how it works. Phi is always measured as an angle at the origin, independent of whether that's the most convenient thing for the question. That's what it is. So these phi slices that look like this, they start where phi is clearly 0, and then they end at, this point right here. We're going to have to figure out what the deal is with this point. And again, lucky break. And please always be on the lookout for this. This kind of thing comes up surprisingly often. But you can think through the givens and persuade yourself that we have an equilateral triangle right there. And so that makes this value of phi, which you'll notice is an angle of that equilateral triangle, pretty self-evident, and so we get pi over 3. So phi goes from 0 to pi over 3. Everybody follow that geometry. Okay. All right, and then again, I'm going to kind of move it along sort of quickly here because a lot of this is repetitious stuff we've done before. So looking at our phi slice, where does rho start? Well, rho starts at that point. And of course, that's actually on this curve, aka it's on this sphere, which of course has a really easy equation. Rho equals 1, and so rho equals 1, solve for rho, it's 1. Then the last slice, this point is on that curve, which is the other sphere, which, again, you can write down the rectangular equation to do all this chapter 1 stuff, plug in the change of coordinates functions, and you can derive that sphere has this equation. Again, solve for rho. Again, lucky break, it's already solved for, and you get that. How are we doing on this latter one? Is everybody happy with that upper bound for rho? Cool. All right. So, the big point on this one was the drawing trick, the 3D visualizing, sort of, circumventing the 3D visualizing, which I think is a nice one. And that kind of finishes part 2 of this monster section 5.5 that we're in. Moving on now to part 3, symmetry theorems. Very underappreciated, in my opinion. I think these are tremendously important. And just by way of example, I'll go ahead and say this now. Maybe I should say it later. When I did my second major in physics way back when, decades ago, I took a lot of physics classes, not unlike a lot of engineering classes, and there were a lot of integrals. Just a ton of integrals to be done in those physics classes. Countless. Right? And my sort of, based on my memories of the experience and all that I had to do there, I think about, this is a conservative estimate, I think about 20% of the integrals that I experienced, I was able to snap my fingers and say, symmetry argument, the integral is 0. Well, I had to take 9 physics classes as part of my undergraduate physics major. That means that nearly 2 entire courses of physics integrals were 0 by symmetry, snap of the finger. This is extremely important, right? This is very, very valuable to know, and I think it's very, very underappreciated, undersold in most multivariable calculus books. So anyway, I want to spend some time talking about this because it's unavoidably that important. So let me remind you how symmetry works. Here's a theorem that I hope y'all all saw in Calc 2. Calc 1, Calc 2, probably Calc 2, but it depends on the course. And that is, if you have an odd function on a symmetric domain, the integral is 0. Hope that looks familiar. Don't forget what an odd function is. Symmetric function, we mean an interval from like negative k to k, where the lower bound and the upper bound are negatives of each other, which, if you think about it, means that any point in the interval, its reflection's also in the interval. Same thing, different phrasing. Okay, why is that theorem true? Well, we can just look at the Riemann sums. Let's look at, in particular, starting off, what is the term in the Riemann sum corresponding to this piece? By the way, notice I'm looking at a graph of a single variable function. Anyway, height times base, etc., and this is the term in the Riemann sum corresponding to that slice. And then what about this piece over here at the exact negative point, negative p instead of p? Well, height times width is, it's this. And then notice that because of the oddness, these two values of f are negatives of each other. That means that these two terms in the Riemann sum are negatives of each other, and when you have two terms in a summation that are negatives of each other, they cancel. And so everything cancels. Every slice on the right cancels with the corresponding slice on the left. So of course the integral therefore adds up to 0. Okay, so that's one way to think about it. Now here's a different way to think about it, pros and cons, but I think as an important point of view, you can also prove it by doing a substitution. Really easy substitution. So remember, we're looking at this integral right here. The substitution that I'm going to choose to make is this right here, x equals negative u. Right, this is basically reflection over the origin, if you will. Right? Now, because of the fact that my interval is symmetric, my domain is its own reflection. Right? If the bounds on the ends are negatives of each other, then flipping takes the one to the other and the other to the one. The interval doesn't change when you reflect. So I can think of this initial integral as actually an integral over an image, because after all, it is its own image. So it's an image. Right? Next, substitution, which of course, as you know, we've spent a bunch of time talking about change of variables, and I'm pushing this point of view of a pullback. Here's where I do a pullback, aka basically a change of variables here. And when you do a pullback, the integral previously over the image gets pulled back to an integral over the pre-image, which is just the original interval I that we're back to now. Don't forget your stretching factor, and I argue that if you are just reflecting, nothing gets bigger or smaller. There's no squishing, there's no stretching if you're just reflecting. So the stretching factor there is 1. Whoops. Alrighty. Then let's not forget about the fact that our function is odd. Our function being odd means that we get a minus sign when we pull out the the negative in the u. Right? That's the definition of what it means for a function to be odd. And check it out, we're basically done. What we have shown by way of this is that this integral is the negative of itself. Different dummy variable, but whatever. Right? So the integral in question, being as it is the negative of itself, that integral must be 0. So lovely little argument. Substitutions allows us to prove this old fact. Again, it's an old fact we knew, right? Again, the reason I visit single variable calculus in class is because I'm going to segue. I'm going to use that as a kind of a launching point to make very analogous arguments in multivariable. So here we go. The analogous idea of reflecting over the origin is just reflecting over a line in 2 dimensions. So a 2-dimensional reflection. Now notice 2 dimensions. We got a lot of elbow room in 2 dimensions. There's so many different directions that you can look in 2 dimensions compared to on the real number line. There's only one direction. So we can choose lots of lines, right? And any of them is kind of in some way analogous to reflecting over the origin in some sense. So with this reflection in mind, I'm going to make the analogous definitions of what do we mean by odd and what do we mean by symmetric. So same basic ideas. Odd symmetry means that you get a minus sign when you reflect. Totally analogous to the definition of odd for a single variable function. And a domain, we say, is symmetric if a point and its reflection are either both in the set or neither in the set. In other words, anytime you have a point in the set, its reflection is also in the set. So that's kind of a Rorschach fold, Rorschach test kind of point of view on symmetry. Okay, so these definitions in mind, we get this awesome brand new theorem, and hopefully very familiar. If you have an odd function and a symmetric domain, your integral is 0. Awesome result. Note, very analogous. In fact, I even wrote it down on the page deliberately to, to even the layout on the page, just like the single variable version of this theorem. Right? It's morally equivalent. It's the same idea. 1 dimension up. Okay. Now, a couple of asterisks. You do have to be careful with this. A lot of students, again, years of experience in teaching multivariable calculus. Here's the big common mistakes that I see students make all the time. Very often, so often, students will see a symmetric domain and think, boom, that alone allows me to conclude the integral is 0. Not so. Very, very importantly, you do need both. Both conditions have to hold. If you only have a symmetric domain and you have not studied carefully your integrand, you got nothing. It just doesn't work. Lots of easy counterexamples. Secondly, you've got to use the same line for both of these conditions. It's not at all sufficient for a function to be odd over one line and the domain is symmetric over a different line. It just does not work, not even close. We're going to see an example to that effect in a few minutes. Okay, so why does this work? Well, again, different points of view. You can take a Riemann sum point of view. Here's a symmetric domain. I've got a line right there, and this is my attempt. Forgive the artistic flaws, but this thing right here is, again, it's intended to have been drawn as symmetric. And you can look at a couple of different points in the Riemann sum. I can look at this point. Keep in mind, if we're looking at a 2-dimensional domain, we're thinking about a 2-dimensional Riemann sum, then we're talking about, like, for example, how much mass is in this region, or how many people live in this region, what have you. And, well, what I get for that point, and what I get for this point, are negatives of each other. And they're negatives of each other because the function's odd, and these 2 points are reflections of each other. So, minus sign means that those terms cancel. Every piece of the domain has a buddy, has a reflected piece on the other side of the line. Everything cancels. We get 0. And now, why do we have this in the section on change of variables? I'm going to show you the other argument, a change of variables argument. Again, the layout on the page, I hope you'll notice, is extremely similar to the layout on the page when we did the single variable version of this. We start off with an integral. Because of the symmetry, our domain is its own reflection. Because we now are looking at an integral over an image, I can do a pullback and pull that back to an integral over its pre-image, again, itself, because of the symmetry. Don't forget your stretching factor. Again, stretching factors are 1 if you're talking about just flipping things over. There's no stretching, there's no squishing. Right? And then again, now we cite the oddness, and because of the oddness, we get a minus sign, and that means that looking at this equation right here, we see that this integral is the negative of itself. Sorry. This integral is the negative of itself. That means that it's 0. So, equivalent argument. The key thing that made it all work, where the money was made here, change of variables. All right, so that's why I have this in the section on change of variables. Okay, alrighty. So let's do one, and to great effect. By the way, this example is pretty awesome in what it allows us to avoid. Look at this nightmare of an integral. Not only is the integrand horrifying, but furthermore, if you think about the domain, it's the region bounded by these 2 curves. Oh my gosh, it's got quartics in it. The algebra on this is going to be brutal, right? Just nightmarish. Nobody wants to crank this out the old-fashioned way. Okay, so I claim we're going to basically do it in a snap. So first observation I'm going to make is that we have our region D is symmetric over the y-axis. Now I'm going to draw a picture here. Again, I think the picture is important. Let's see here. We've got there's our axes. I'm going to draw these 2 curves. First, I'll draw this quartic. Single variable calculus. Y'all remember how to draw polynomials. This ends up being something kind of like this. And again, forgive the bad art, but something kind of like that. And then now let me draw this other line, y equals -1. Well, that's something like this. And just from what I've drawn, I think you'd be willing to believe, perhaps, that this shape is symmetric. I certainly drew it as being symmetric looking, specifically and importantly, let's see here, color choices, symmetric over the y-axis. It's not symmetric over the x-axis, right? It's not symmetric over a 45-degree line, the y-axis specifically. Is everybody with me? Okay. Now, if you're not sure you believe this, if you're concerned, for example, about how do I know that this curve that I drew has the symmetries that I claimed, well, I'll make the following observation down here. If you look at the formula for the reflection, right, looking at this orange line and thinking about how points reflect. When you reflect over that line, you just get a minus sign on the x-coordinate. Well, if you then take that reflected point and plug it into the equation, notice the equation doesn't change. Right? You have the same equation here as we had in the first place. And what that means is that anytime you have a point on your curve, the reflected point also on the curve because the reflected point also satisfies the equation. And that means we have a symmetric curve there. So that's the argument. Now you don't have to actually give me those arguments. Symmetry arguments for a domain, I think, are usually, if when they're true, are pretty at a glance kind of clear, right? So, but if you really are wondering how did I know, or what was my thought process that allowed me to conclude that this blue curve is symmetric, that's the reasoning. Okay, so we've got ourselves a symmetric domain. I claim we have an odd function. I claim f is odd, and this is something that requires some doing. Right? Remember our definition of odd. Function is odd if, when you plug in the reflection, the upshot to the value of the function is just a minus sign. Right? This is what we mean by odd. Reflecting the input gives you a minus sign on the output. So let's check and see if that holds. Well, here's the algebra. I'm going to take the reflection, plug it into the function, and compute, algebra, and note, sure enough, we get a minus sign on the value of the function. And that's the only effect of reflecting the input, is just that minus sign. How are we doing? Is everybody with me? Okay. Now, notice I just yada significant amount of algebra. Make sure that you're comfortable with this algebra. A couple of things to make note of. When you plug in this reflection, keep in mind our reflection is negative x comma y, right? And we're plugging this into our integrand. This goes into there. Don't forget that our first input coordinate is negative x, right? And it's confusing because up in the formula for the function, we use x as the first input. So you just have to remember as you're doing this that negative x goes in place of x. Right? So be careful with that. That is easy to kind of mess up and accidentally, you're just kind of transcribing and you might accidentally forget, I forgot to plug in that minus sign. Okay, so heads up on that. And then do be careful with your algebra. It's easy to kind of, lose a minus signs. You got to make sure to count correctly, right? And then also don't forget stuff like this. Don't forget stuff like this. For example, that sine is established as an odd function. Right? So sometimes you have to use these kinds of previously established facts. Yeah. Mm-hmm.
Since it's symmetric over the y-axis, that's why we're plugging in the negative x and not the y.
Yeah, well, that's right. So I'm citing symmetry over the y-axis, and because I'm going over the y-axis, when you see it in the picture, right, that's what allows me to understand what the reflection looks like. And seeing geometrically what the reflection looks like is how I'm able to write the formula for the reflection. Does that answer your question?
Yeah.
Yeah. Cool. Okay. Now, so we're done. We win integral of 0 by symmetry, and didn't have to deal with antiderivatives of this, thankfully. Right? What a nightmare that would have been. I don't have to deal with the fact that my domain's got a lot of ugly in it, which would get into my bounds, which would get into my next integrand. Nope. All that goes away. Poof. Answer 0. We're done. Massive win. Huge victory. Is everybody? Yeah, okay. All right. So please do notice that there were several things that had to be said here in order to make a complete argument. I did have to tell you, if I'm going to talk about symmetry and oddness and stuff like that, we've got to talk about over what line. Right? There's lots of lines over which a domain could conceivably have symmetries, or a function could conceivably be odd. So you got to tell me what specific line are you talking about. We then also need to see the formula for the reflection, because that plays a critical role in determining the next steps. You've got to make the observation that f is odd. You also have to be right about that. You can't just claim something's odd and say, well, I have 20% credit because I claimed it's odd. If it's not odd, then that's not worth anything. And then notice, I had to demonstrate that f is odd. That's not obvious, right? There's a substantial amount of work that goes into determining if a function is odd. Sometimes more than others, but still, I mean, it's a significant part of the reasoning. You got to give that to me. And then finally, the domain's got to be symmetric. So again, you've got to correctly note that the domain is symmetric. Again, correctly, if it's actually symmetric. So these are the 5 things you will notice conspicuously absent from this is you don't have to prove that the domain is symmetric. It's fine to just note it. Proving it it's usually at a glance pretty clear. This isn't a proof class. If this were Math 222, maybe I'd feel differently. But in a class like Math 219, just observe it. But again, you gotta make that recognition because the symmetry of the domain is a key part of the reasoning. You gotta give that to me. Okay, but don't bother proving it. Okay. And then just a last little heads up, I do think that it is a risky move. There is a risk to using a symmetry argument. Here's why. Let's suppose you claim symmetry, but something about it you've misunderstood, and in fact, the domain's not symmetric, or the function isn't actually quite odd. Right, it's all the terms but one, or something like that. Right? If anything goes wrong in the argument, the whole point is there is no argument there at all in the first place. So a symmetry argument, where the symmetry argument doesn't actually work, is not actually progress toward a solution. It's just writing down a bunch of stuff that goes nowhere. So the danger, again, very, very danger. Risky thing is make sure you're right. If you're going to use a symmetry argument, double check it. Think carefully. Don't just kind of fast and loose. Make symmetry arguments. You got to be really careful because they're I don't want to say there is no partial credit, but there's not much partial credit, if any. Just because, again, the nature of if it doesn't work, then it's not heading toward anything actually valid. So, very risky. Heads up. Do be careful. All right, here's an example. Now, this is an example of what not to do. This integral right here, there is, in fact, a symmetry argument that shows that this integral is indeed 0. And let's imagine now that a student writes down this right here, and gets the right answer, as it were, right? Concluding correctly that the integral is 0. Well, again, keep in mind this class is not about answers. This class is about reasoning, and this reasoning is sadly deficient. There's a lot of gaps in this reasoning. Let's go through the list. Coming back up to here. The line of symmetry. What line of symmetry is it that the student claims that the domain has a symmetry and that the function has odd symmetry, but over what line? I don't even know what line we're talking about. Right? So that's sadly missing. Let's see. The student has not demonstrated that the function is odd. The student has claimed that the function is odd. Didn't demonstrate it. It's really not obvious that a function is odd. So again, that's missing. The student also never wrote down the formula for reflection, right? Which would be important for demonstrating oddness. So this student's done 2. The student has observed that f is odd and has observed that the domain is symmetric. So the student has done 2 of these 5 required. So I would expect, what would that be? 8 out of 20 on this, right? Or 4 out of 10, or because the argument just isn't there completely. How are we doing? Is everybody? I mean, I do this example because I want to make sure students understand what I'm expecting and how important it is to give me that reasoning. Just so there's no ambiguities on what to expect on exams. Okay. And are we out of time already? Man, time always flies on Symmetry Day. Okay, we'll pick up here on Monday. Oh no, spring break. We'll pick up here in forever from now. Okay, see y'all later. Have a great spring break, everybody.